はい、では始めます。私は、古賀先生です。それから、コンパス。ここにコンパスがあります。コンパスの、リンク、YouTube リンク載ってます。それからブルーキャット。ブルーキャットから言っても、ここに、リンクが載ってます。YouTube リンク。YouTube リンク載ってます。それから、Twitter からも YouTube リンクが載ってます。それで、テキストは、ここのギガファイル、あるいはコンパスからもあります。テキストはテキスト in PDF っていうのがあります。で、ここでダウンロードできます。で、なんだっけ、あれ開かないの。開いたのかな。どうやって開くの。もう一回やんなきゃいけない。開きます。それで、今日は331ページからです。331ページ。ハミルトニアンがこういうふうになりました。で、rewriting the Hamiltonian this way and that way may seem like an exercise in futility. 無駄なエクササイズのように見える。But trust me, it's not. First of all, the last term is just an additive constant that adds to the numerical value omega h bar divided by 2 to every energy eigenvalue. We can ignore it for now. Later, after we've solved the rest of the problem, we can add it back in. The guts of the problem are found in the expression p plus I omega x, p minus I omega x. It turns out that these two factors, p plus I omega x and p minus I omega x, have some very remarkable properties. In fact, they are the raising and lowering operators, or creation and annihilation operators, that I told you about earlier. For now, these are just names, but as we go along, we will see that the names were well chosen. The obvious definitions would be A minus. This one. The first part, this is A minus. This is A minus definition. And the other for the lowering operator, and A plus is definition. Minus, plus, this one. For raising operator, but history sometimes preempts the obvious. Preempts 選取する。変わる、置き換える、選取する。History sometimes preempts the obvious. Historically, the raising and lowering operators have been defined with an extra factor in front of them. まあ歴史が優先するってことです。おそらくはこういうふうに、A-A+をこのように定義していた方が、分かりやすかったんだろうけれども、歴史的には別の定義が使われてしまっていて、そっちの方が優先しているっていうことね、多分ね。Historically, the raising and lowering operators have been defined with the extra factors in front of them. Here are the official definitions. A minus, there is a minus I. I in front. Square root 2 omega h bar. Then there is a minus I in front for A plus. Divided by square root 2 omega h bar. P minus I omega x and P plus I omega x. If we use these definitions, the Hamiltonian starts to look very simple. H become omega h bar A plus A minus plus 1 half. I think we can just plug in 2 omega h bar 2 So because this thing is 2, let me see, this 2 omega h bar 1 P plus I omega x P minus I omega x then we can multiply this. So here we multiply. So original expression is recovered. There are only two properties of A plus and A minus that we need to know. The first is that they are Hermitian conjugates of each other. Hermitian conjugates of each other. That follows from their definitions. Okay, I can show you P. So I think we have to do this way. We have to do this way. A plus is square root 2 omega h bar minus I. Was it minus I? Sorry. Minus I 2 omega h bar P plus I omega x. Then we consider Hermitian conjugate. Hermitian conjugate. Hermitian conjugate is like this. A plus, here it is dagger equal, you change I to minus I, so you change 2 omega h bar I. Then you have P dagger minus I omega x dagger. Then this P dagger, this is, you can omit because P dagger equal P, x dagger equal x. This is called Hermitian. P and x Hermitian. Okay, these are Hermitian. So you see a Hermitian conjugate of A plus. Hermitian conjugate of A plus become A minus. Because you see there is no minus sign in front. This is no minus sign in front, and a minus sign in the parentheses. The other, okay, this is the first property. The first is their Hermitian. The second property is what really gives them juice. The commutator of A plus and A minus is 1. This commutator of A plus and A minus is 1. This is easy to prove. First, we use the definition to write A minus, A plus is 1 over 2 omega h bar p minus I omega x, comma p plus I omega x. The next step is to use the commutation relation x comma x equals 0, p comma p equals 0, and x comma p equal IH bar. Apply these to the above equation and you will quickly find that a minus, comma a plus equal 1. We can make the Hamiltonian in equation 1022 even simpler by defining a new operator n equal a plus a minus which is called a number operator. Once again, this is just a name, but as we will see, it's a very good name. Stated in terms of the number operator, the Hamiltonian becomes h equal omega h bar times n plus 1/2. So far, all we have done is define some symbols, a plus, a minus, and n, that make the Hamiltonian look deceptively simple. It's not clear that we are actually any closer to figuring out the energy eigenvalues. To proceed further, let's recall my earlier advice. Whenever you see two operators, commute them. In this case, we already know one commutator, a minus a plus equal 1. Next, let's find the commutator of the raising and lowering operators with the number operator n. We will do this by brute force.しらみつぶし。Here are the steps. A minus comma n equal a minus n minus a na minus a minus a plus a minus minus a plus a minus a minus. Now we will combine the term in the form a minus a plus minus a plus a minus a minus. Anyway, this looks complicated until we notice that the expression in the parentheses is just a minus comma a plus, which just happens to be 1. Using this fact to simplify, we get a minus n equal a minus. We can do the same thing with a plus and n. The result is almost the same except for the sign. Here is the whole list of commutators in one neat package. A minus plus a minus a plus commutator is 1. The commutator a minus n equal a minus. The commutator a plus comma n is a minus minus a plus. Okay, I think better way to write this is this. You can write n a plus equal a plus n a minus minus a minus. So this looks as if eigenvalue problem. See, this one resembles eigenvalue problem. Because this, you can see here, a plus eigenvalue is plus 1, a minus a minus eigenvalue is minus 1. So this resembles eigenvalue problem. This is what you might call a commutator algebra, a set of operators that closes under commutation. Commutator algebras have wonderful properties that make them one of the theoretical physicists' favorite tools. We are now going to see the power of this commutator algebra in the iconic example of the harmonic oscillator, using it to find the eigenvalues and eigenvectors of n. Once we know these, we can immediately read off the eigenvalues of h from equation 1023. The trick is to use a kind of induction procedure. We begin by supposing we have an eigenvalue and eigenvector of n. Call the eigenvalue n, small n, and eigenvector ket of small n. By definition, n small ket of small n equal small n ket of small n. Now let's consider a new vector obtained by acting on ket of small n with a plus. Let's prove that the result is a different eigenvector of n with a different eigenvalue. Again, we accomplish this by straightforward application of the commutation relations. We will start by writing the expression n of a plus ket of small n in a slightly more complicated form. N of a plus ket of small n equal so this one you can see. If you remove parentheses, if you remove this one, this becomes plus, and you can cancel this as this. So left hand side and right hand side become same. So this is same. The expression in bracket on the right hand side is the same as NA plus, which with the term A plus N added and then subtracted. But notice that the expression in parentheses is the last of the commutators from equation 1025. If we plug that in, we get So I think this is 1. No. N plus N minus NA plus. This is A plus N minus NA plus. This is minus A plus. So this is minus A plus. So you have A plus N plus 1 N, which is equal to A plus N plus 1 N, which is equal to N plus 1 A plus N. Then you can compare this thing and this thing. So now you have N A plus N equal N plus 1 A plus N. See? Then this is the Eigenvalue problem. This is the operator and state vector. This is the eigenvalue state vector. Actually, eigenvector. So the eigenvalue for large N is small n plus 1. And the eigenvector for this equation is this. A plus applied on ket of small n. You plug that in, we get this equation. The last step is to use the fact that ket of small n is eigenvector of number operator n with eigenvalue of small n. That means we can replace large n plus 1 with small n plus 1. Large n A plus n equal small n plus 1 A plus n. A plus ket of n. As always, when we run on autopilot, we have to keep our eyes open for interesting results. Equation 1026 is interesting. It says that autopilot. Anyway, it says that the vector a plus k of n is a new eigenvector of large N with eigenvalue small n plus 1. In other words, given the eigenvector k of small n, we have discovered another eigenvector whose eigenvalue is increased by 1. All of this can be summarized by the equation a plus k of n is k of n plus 1. Obviously, we can do this again and again to find the eigenvalues n plus 1, n plus 2, n plus 3, and so on. Remarkably, we find that if there is an eigenvalue n, there must be an infinite sequence of eigenvalues above it, spaced by integers. The name raising operator seems very well chosen. What about a lowering operator? Now, surprisingly, we find that a minus n produces eigenvector whose eigenvalue is 1 unit lower. A minus k of n is n minus 1, k of n minus 1. This suggests that there must be an ending sequence. Okay, let me stop here. 3